Hi! This week was an introduction to the basics of geometry. You have seen a lot of terminology and many important results. Let's do a recap. First of all, to be able to do calculations in geometric problems, coordinates are of fundamental importance. In the plane, the idea is to associate a pair of numbers to every point to describe its location. René Descartes introduced a systematic way to do this. Pick two orthogonal lines in the plane, endow each with a direction and a scale of units. Then from the point where the lines intersect, called the origin, we can reach each point by first moving parallel to the first line and then moving parallel to the second. The coordinates of the point reached are precisely the displacement along the first and second line respectively. This setup is called a Cartesian coordinate system. Using this, we can translate geometric questions into algebraic questions. Another fundamental concept is that of a vector. You have seen that a vector is an object with a magnitude and a direction. It is usually represented by an arrow. Vectors can be used to model physical quantities like force, velocity, and displacement. There are several operations that you can perform on vectors. First of all, two vectors can be added. The sum of two vectors is obtained by putting one after the other. You can also multiply vectors with a scalar. This comes down to changing the length and possibly flipping the direction of the vector, in case the scalar is negative. Using coordinates, vectors can be described using numbers called components. Using these components, we can perform vector operations algebraically. Adding two vectors comes down to adding them component-wise. Indeed, if we take the vector 4, 3, and we put the vector 1 minus 2 after it, we get the vector 5, 1. Scalar multiplication comes down to multiplying component-wise. For example, if we multiply the vector 3, 2 by 2, we get the vector 6, 4. Additionally, we can define another operation on vectors, the dot product. This product is defined as follows. The dot product of vectors AB and CD is given by AC plus BD. Armed with these concepts, we can do calculations. For example, in the Cartesian coordinate system, the distance between 2 points can be calculated in terms of their coordinates. The length of a vector, also called its norm, can be calculated using the dot product. Finally, there is a surprising relation between the dot product of two vectors and the angle between them. The dot product of two vectors equals the product of the norms times the cosine of the angle between them. This relation can be used to find the angle between two vectors. Also, you can use it to detect orthogonality. Two vectors are orthogonal precisely when their dot product is equal to 0. We then moved on to describe curves in the plane. First, you saw that curves can be described by an equation, also called an implicit description. For example, any circle can be described by the given equation. Here A and B are the coordinates of the center of the circle and R is the radius. Similarly, any line can be described by an equation of the form ax plus by equals c. Here AB is a vector orthogonal to the line and c is determined by any point on the line. Another way to describe curves is by means of parametrization. Think of a mouse moving along the curve. The x and y coordinate of the mouse are both functions of time. These functions, together with the appropriate parameter interval, completely describe the curve. Remember that each part of the curve should be covered exactly once, except possibly for isolated points. So a mouse moving back and forth on a curve does not provide a valid parametrization. A useful property of parametrizations is a relation to moving objects. The motion of an object can be described by coordinate functions. The first and second derivative of the coordinate functions then give the velocity, speed, and acceleration of the object. In the exercises, you encountered some standard parametrizations, which we recall here. For a circle with center AB and radius r, a parametrization is given by x of t equals a plus r times the cosine of t, and y of t equals b plus r times the sine of t, with t between 0 and 2 pi. The line segment between points AB and CD can be parameterized by x of t equals a plus c minus a times t, and y of t equals b plus d minus b times t, with t between 0 and 1. And the graph of a function f on an interval a to b can be parameterized by x of t equals t, and y of t equals f of t, with t between a and b. Finally, we considered what changes if we go from geometry on the plane to geometry in space. The surprising answer is not much. Most of the concepts and results that we have seen easily generalize by simply adding one coordinate or component. Points are described by 3 coordinates and vectors have 3 components. Formulas for addition and scalar multiplication are the same. The dot product easily extends, and the formulas for norms and angles in terms of the dot product still hold. Of course, curves and surfaces can have more exotic shapes, but we can still describe them using equations and parametrizations. These were the main topics of this week. If you feel uncertain about some of the topics, don't hesitate to have another look at the videos or exercises. Good luck with the homework.